When we talk about the birth of a planet, it's easy to imagine something slow, abstract, almost symbolic. But in reality, it is a violent, glowing, chemical event. At the very beginning there is no ocean, no rock, no sky, a collapsing cloud of gas and dust swirling around a newborn star. Every mountain, every grain of sand, every cell that will ever live on a world like ours starts out as microscopic dust, heated, melted and reshaped in the furnace of a young system. For decades, astronomers have studied this process from a distance, always arriving a little too late. They saw mature planets, or well-formed disks with clear gaps and rings where planets must already exist. What they had never truly seen was the raw, first step. The moment when dust begins to turn into solid, mineral-rich material, the seeds from which a planet can grow. That is what makes the recent observations of the young stellar system HUPS 315 so extraordinary. Deep inside the Orion complex, roughly 13 to 1400 light-years away, a very young protostar is still wrapped in its natal cocoon of gas and dust. Around it, a disk of material is rotating like a flattened whirlpool, the classic protoplanetary disk we see in artist impressions and simulations. But with the combined power of the James Webb Space Telescope and the ALMA radio array, astronomers have, for the first time, caught evidence that the dust in this disk is doing something new. The silicate-rich grains are being heated to extreme temperatures and then cooling into solid, glassy minerals. This is not just dust in a disk anymore. This is the beginning of rock. In our own solar system, we infer that something similar happened more than 4.5 billion years ago. The inner disk around the young sun must have been hot enough to melt silicates, forming chondrules and other high-temperature components that later became part of asteroids and planets. We see their fossil remains today in meteorites, but we do not see the process itself. We reconstruct it from fragments. Around HUPS 315, by contrast, we are catching that furnace in action. JWST, looking in the infrared, detects spectral fingerprints of hot minerals in the dusty environment. ALMA, observing at millimeter wavelengths, reveals how the larger grains are starting to clump and settle. Together, they give us a direct snapshot of the transition from chaotic dust cloud to structured, mineral-rich building blocks. In more poetic terms, HUPS 315 is a baby star still wrapped in its blanket, and we are watching the first bricks of its future planets being fired in a cosmic kill. The star is young enough that it has not yet cleared its surroundings. The environment is still thick, turbulent, and opaque in visible light. But infrared photons slip through, carrying the story of what is happening inside. The minerals that are now forming will, over millions of years, collide, shatter, reassemble and grow into kilometer-sized planetesimals. Those will merge into planetary embryos, and eventually, given enough time and stability, into full-grown worlds with surfaces, atmospheres, maybe even oceans. What Webb and ALMA have shown us is the very first frame of that long evolutionary movie, the moment the dust decides it will become stone. This is why many astronomers compare this discovery to a baby photo of our own solar system. HUPS 315 is not a twin of the Sun, and its planets will not be copies of Earth, but the physics is the same: gravity pulling dust inward, heat transforming minerals, collisions and coagulation building up structure grain by grain. For the first time, we are not just inferring these steps from theory and ancient meteorites, we are watching them unfold, in real time, around another star. The video you are about to watch is an invitation to linger inside that process, to imagine the glow of the disk from the inside, to feel the heat of newborn minerals, and to remember that everything familiar about our own world once passed through a stage very much like this. In the classical story of planet formation, everything begins with a young star wrapped in a broad, flattened disk of gas and dust. The star itself has just formed from the collapse of a giant molecular cloud, and the leftover material does not simply vanish. It settles into orbit, forming a spinning, pancake-shaped structure called a protoplanetary disk. At first, this disk is chaotic and hot, full of microscopic grains of silicates, carbon, and various ices swirling in circular paths around the newborn star. These grains are unimaginably small, more like smoke than sand, yet they are the seeds from which entire worlds will eventually grow. As the disk cools, temperature begins to carve it into zones. Very close to the star, only the most refractory materials, tough silicate minerals and metals, can survive as solids, while farther out, water, methane, and other volatile substances freeze into icy grains. This simple temperature gradient sets the stage for everything that follows: rocky planets inside, icy bodies, and gas giants outside. Within this disk, gravity is not the only player. Tiny dust particles constantly collide, driven by turbulence in the gas and by their slightly different orbital speeds. Most of these collisions are gentle. Instead of shattering, grains stick together through electrostatic forces, growing from submicron dust to slightly larger clumps, the so-called pebbles, still only millimeters to centimeters across. It is an incredibly fragile phase of growth, a balance between sticking and fragmentation, between being pulled inward toward the star and surviving long enough to grow. Over time, regions of the disk become enriched in these pebbles. Pressure bumps, vortices, and subtle variations in gas density act like cosmic traps, gathering pebbles into narrow rings and arcs. Inside these traps, the local density of solid material rises dramatically, and gravity begins to wake up on small scales. Clumps of pebbles collapse into kilometer-sized bodies called planetesimals, the first objects large enough to have their own meaningful gravity and to withstand minor impacts. From this point, the growth accelerates. Planetesimals collide and merge in a process sometimes described as runaway accretion. Once a body becomes slightly larger than its neighbors, its stronger gravity allows it to sweep up nearby material even more efficiently, quickly turning a scattered population of small objects into a hierarchy of a few dominant ones. These larger bodies are the planetary embryos, ranging from moon-sized to Mars-sized, carving gaps and stirring the disk as they orbit. In the inner disk, they assemble into rocky planets by repeated violent mergers. In the colder outer regions, some cores become massive enough to capture huge envelopes of hydrogen and helium before the gas disperses, forming gas giants. The entire transformation, from dust to mature planets, takes a few million to perhaps 10 million years. But the very first phase, when hot gas cools just enough for the first solid silicate grains to condense out, when the disk transitions from pure vapor to a mixture of gas and solid mineral seeds, is much shorter, lasting perhaps only 100 to a couple of 100,000 years. It is brief, deeply buried inside dense dust, and almost always hidden from our telescopes. Until now, most of our observations have caught disks after rings and gaps have already formed, or full planetary systems long after their violent youth is over. What makes the new observations so remarkable is that they don't show us the end of the story, but that elusive time zero, the moment when dust first becomes stone, and a planet's history truly begins. HOPS 315 is tucked deep inside the Orion star-forming region, in a place where space is not empty and black, but thick and glowing with cold gas and dust. This is not a mature star like our Sun. It is more like a heartbeat that has only just begun. Astronomers classify HOPS 315 as a protostar, a young object still in the process of collapsing under its own gravity, shrouded in the leftovers of the cloud from which it was born. Around it, a dense, rotating envelope of gas slowly funnels material into a flatter, spinning structure, the protostellar disk. That disk is the cradle of future planets, the raw construction site of an eventual planetary system. Normally, this entire region is hidden from our view. Dust absorbs visible light and even much of the infrared, turning the birthplace of planets into an opaque cocoon. In the case of HOPS 315, however, nature is unusually generous. There is a kind of accidental window in the surrounding cloud, a less dense line of sight that lets us peer straight into the inner regions where temperatures are high, densities are extreme, and chemistry is changing from simple gas to complex solids. This is where JWST and ALMA come in. JWST, looking in the mid-infrared, is exquisitely sensitive to the glow of hot dust and specific spectral fingerprints of minerals. ALMA, observing at millimeter wavelengths, traces the colder dust and gas structures that wrap around the central protostar. Together, they reveal that HOPS 315 is not just a star in the making. Its inner disk already contains freshly formed, high-temperature silicate grains, tiny droplets of rock that have condensed out of the gas close to the protostar, where temperatures can reach hundreds to more than 1,000 Kelvin. These droplets are the very first seeds from which pebbles, boulders, planetesimals, and eventually rocky planets can grow. The distance, roughly 1,300 to 1,400 light-years, adds a quiet sense of perspective. When these structures were forming, complex life on Earth did not yet exist, and yet the physics is the same that once acted in the disk that produced our own world. In HOPS 315, we are essentially seeing an echo of our own past, a young, sun-like object wrapped in its dusty cradle, beginning to sort that dust into hot inner regions and cooler outer zones, laying down the first layers of a planetary architecture. It is not yet a system with clearly defined planets, No orbits you could name, no worlds you could map, but the essential ingredients and temperature gradients are already there. The discovery is so powerful because it catches this system at a fleeting stage, the moment when gas is still dominant, but solids are being born, when the star is still swallowing material, but the disk is already quietly starting to build future planets. It is as close as we have ever come to a time-stamped snapshot of planetary construction right at the beginning. ALMA and JWST are two completely different kinds of eyes, tuned to different colors of the universe, and yet together they form a single, coherent picture of how worlds begin. ALMA, the Atacama Large Millimeter Submillimeter Array in Chile, is a network of high-precision radio antennas spread across the high desert. It is exquisitely sensitive to cold dust and molecular gas, the raw material from which stars and planets are built. In the case of HUPS 315, ALMA maps the large-scale structure, the envelope of gas still falling onto the young star, the broad, rotating disk of material around it, and the outflows and winds that are already beginning to carve cavities through the surrounding cloud. In ALMA's vision, the system looks like a sculpted, rotating structure of cold matter, streams of carbon monoxide tracing spiral motions, extended emission revealing where the bulk of the mass still resides. You see the construction site from above, where the gas is densest, how it flows, how it feeds the young star and its disk. JWST, by contrast, is a warm, infrared eye in space, free from Earth's atmosphere and tuned to the glow of dust and molecules heated close to the protostar. Where ALMA is sensitive to the outskirts and the cold skeleton of the system, JWST zooms into the inner, hotter regions, the place where temperatures are finally high enough to transform gas into solid mineral grains. Its mid-infrared instruments pick up the spectral fingerprints of silicates and other high-temperature condensates, revealing that right next to HUPS 315, the gas is beginning to crystallize into droplets of rock. In JWST's view, the inner disk is not just a vague blur, it is a chemically structured environment, with specific minerals forming at specific distances from the star. That inner zone is where the first hard seeds of future planets are literally being forged. The breakthrough comes from overlaying these two visions. ALMA tells you how much material is available, how it flows, how the disk and envelope are shaped on scales of tens or hundreds of astronomical units. JWST tells you what is happening on the small scales that ALMA cannot resolve, where the dust heats up, when it transitions from amorphous grains to crystalline silicates, how close to the star the building blocks of rocky planets first appear. Without ALMA, you would see the glowing minerals but not understand the global architecture they live in. Without JWST, you would know there is a disk, but not that its inner regions are actively condensing rock. Together, they turn HUPS 315 from a vague young star with a disk into a detailed laboratory, gas flows, temperature gradients, and the very first solid grains captured at the same time. This is why astronomers call it a true multi-wavelength portrait of planetary birth. Two instruments, two very different bands of light, one shared story about how dust becomes a world. Inside the dusty cradle of HUPS 315, JWST did not just see a vague glowing disk, it saw stone being born. Through its infrared eyes, the telescope split the light from the region around the young star into a spectrum and found the unmistakable fingerprints of solid minerals and vaporized rock. Bright, sharp features from crystalline silicates appeared in the data, minerals like magnesium-rich olivine, forsterite, the same family of minerals we find today in meteorites and in some of Earth's mantle rocks. These are not abstract dust grains, they are the first solid bricks of a future rocky world, glowing because they are still warm from their violent birth near the star. Even more revealing was the signature of silicon monoxide gas. To see SiO in such abundance so close to a forming star means that rock has actually been heated until it vaporizes. In the inner disk, temperatures can rise so high that silicate grains no longer remain solid. They evaporate into a gas of metal oxides and silicates. As that gas flows slightly outward or cools just enough, it begins to condense again into microscopic crystals, a kind of stone rain, falling through the inner regions of the disk. This is the phase we almost never catch, the moment when dust stops being an abstract word and becomes real, specific minerals that can clump, collide, and slowly grow into pebbles, boulders, planetesimals, and eventually planets. What JWST is seeing around HUPS 315 is essentially a chemical factory at full speed. The hot inner disk, bathed in the star's radiation, is constantly cycling material between solid and gas. Grains spiral inward, heat up, evaporate, vapors cool and crystallize, newly formed crystals are lofted, mixed, and transported. Over time, this process sorts and refines the raw material, just as it once did in the inner solar system. We know that meteorites in our own system contain the same types of high-temperature silicates, locked into tiny glassy inclusions that were once molten droplets in the young solar nebula. The spectrum of HOPS 315 looks like a live replay of that distant epoch, the same minerals, but still in the furnace stage. There is something almost intimate in this view. We are not just looking at a faint ring or a dark gap, we are watching the very first solids appear in the glow of a newborn star. The gas in this region is so hot and dense that it is hostile to anything fragile, yet out of that violence the basic ingredients of continents, mountains, and rocky cores begin to crystallize. In a few million years, if the system survives, those grains could be part of a terrestrial planet with a surface, an atmosphere, maybe even oceans. For now they are just dust, but dust with a destiny. JWST has caught them at the moment when they are crossing that invisible line between formless gas and solid stone, between potential and structure. It is as close as we have ever come to seeing the first heartbeat of a rocky planet. Around HOPS 315, ALMA is not just taking a pretty picture, it is dissecting the physics of a forming planetary system in real time. When astronomers pointed the array of radio antennas in Chile toward this baby star in Orion, they did not just see a vague blob of emission. They resolved a young protostar surrounded by a compact disk and, emerging from it, powerful flows of gas that tell the story of how material is being rearranged, heated, and sometimes ejected before planets can fully form. In the maps of carbon monoxide, CO, the system looks like a kind of celestial butterfly, two opposing lobes of molecular gas, one moving slightly toward us, the other slightly away, forming a bipolar outflow that opens a cavity through the surrounding cloud. This is the breath of the infant star, a disk system, a wind driven along the polar axis that carries away angular momentum and excess material so that some of what remains can quietly settle into the disk and eventually into planets. Closer in, ALMA traces something even more violent, a narrow, collimated jet rich in silicon monoxide, SiO, a molecule that appears when dust grains containing rock-forming elements have been shattered, vaporized, and then reassembled in shocked gas. This SiO jet shoots out from the immediate neighborhood of HOPS 315 like a high-speed needle, marking a region where gas slams into gas at hundreds of kilometers per second. Those shocks are energetic enough to rip apart solid grains, release their elements into the gas phase, and then allow them to cool and recombine. In other words, the very same process that JWST sees in infrared spectra as evaporated rock and newly forming crystalline silicates is being outlined by ALMA in the language of millimeter-wave emission lines. The radio view and the infrared view are two faces of the same phenomenon, a young system busily melting and reforging the raw materials of future worlds. The shape and strength of the CO outflow tell us that HOPS 315 is still in a vigorous accretion phase. Gas is spiraling inward through the disk toward the protostar, and part of that infalling material is being diverted into wide, sweeping winds that blow away from the system's poles. These winds carve out low-density channels in the surrounding cloud, making it easier for high-energy radiation and jets to escape. That, in turn, regulates how much cold gas is left in the disk and how long the disk can keep feeding both the star and any forming planets. Too strong an outflow, and the disk will be stripped bare before massive planets can grow. Too weak, and the system may stay too hot and turbulent for solids to settle. ALMA's CO data, showing the velocity and extent of the outflow, therefore become a kind of live diagnostic of how delicately balanced this early phase really is. The SiO jet is even more directly tied to the very innermost regions where rocky planets are destined to emerge. Because SiO is produced in shocks that process silicate dust, its presence tells us that solid, rock-forming material is already part of the story. In the vicinity of the protostar, temperatures rise high enough for that rocky material to vaporize. Farther out along the jet and within the disk, it cools and condenses back into tiny crystals. By seeing the SiO jet and the CO outflow together, astronomers can map how energy injected near the star propagates outward, reshaping both gas and dust. ALMA effectively shows the pathways along which raw rock is transported and transformed before it ends up as the building blocks of planets. Put together, the ALMA view around HOPS 315 is not just a static snapshot of a disk. It is a dynamic, three-dimensional flow pattern, a flattened, rotating reservoir where planets will eventually form, broad molecular winds that regulate how much material is available, and razor-thin jets that reveal where rock is being shock processed at extreme speeds. When you place this radio portrait alongside JWST's infrared detection of hot silicate vapor and newly condensing crystals, you get something unprecedented, a physically consistent, multi-wavelength picture of the moment when a system first begins to turn gas and dust into solid planetary ingredients. For the first time, we are not simply inferring that planets will form there someday, we are watching the factory turn on. Catching a planetary system at time zero is like walking into a workshop at the exact second the first spark flies from the tools. In theory, astronomers have understood for years that the earliest phase of planet formation must happen very quickly. In just 100 to a couple 100,000 years, a young star's surrounding gas goes from being a smooth, hot cloud to a place where solid grains of rock and metal first condense, collide, and begin the long journey toward becoming pebbles, boulders, and worlds. That sounds like a long time on a human scale, but compared with the multimillion-year lifetime of a protoplanetary disk and the billions of years a star can shine, it is almost nothing. Statistically, the odds of pointing a telescope at exactly that short phase, in exactly the right system, and with enough sensitivity to see what is happening, are incredibly small. Most of the time, the young stars where this process occurs are buried in thick, opaque cocoons of dust. Their light is heavily absorbed and scattered. We may detect their rough presence from far infrared or radio emission, but the innermost region, the few astronomical units where rocky planets will eventually live, is completely hidden. We see the consequences at a distance: broad molecular outflows, jets punching cavities in the surrounding cloud, and, in somewhat older systems, beautiful rings and gaps carved in the disk. But the actual transition from hot gas with dust suspended inside it to solid mineral grains condensing out and beginning to fall like a rocky rain has always happened behind the curtain. By the time the region is transparent enough to look into, that first condensation step is usually already over. The solids have cooled, grown, and moved on to the next stages. HOPS 315 is an exception because almost all of the unlikely conditions line up in our favor at once. The system appears to be at just the right age. The protostar is still deeply embedded, still driving strong outflows and jets, but its inner disk has already heated up to the point where rocky material is beginning to evaporate and recondense. Around it lies a dense molecular cloud as usual, but in this case there is a partial opening, a natural window in the dust, that allows the combined power of JWST and ALMA to peer directly into the engine room. JWST's infrared eyes can pick up the spectral fingerprints of hot silicate vapor and freshly forming crystals close to the star, while ALMA maps the surrounding flows of gas that feed and shape the disk. The system is also located in a region of the sky where long, deep exposures are practical, and at a distance close enough that these subtle signals rise above the noise. When you put these pieces together, you start to see why this observation is being described as catching time zero for planet formation. It is not simply another protostellar disk, not just another pretty infrared nebula. For the first time, we are witnessing the moment when diffuse gas and dust are measurably turning into solid planetary material in a very young system around another star. The silicate vapor seen by JWST is not an abstract chemical curiosity. It is the direct sign that rock is being melted, vaporized, and then cooled into new grains that will, over millions of years, be assembled into planetesimals and, eventually, planets. The jets and outflows mapped by ALMA are not just dramatic structures. They are part of the machinery that stirs, heats, and redistributes that same material. Most young stars that go through this phase will never show it to us so clearly. They will be too embedded, too distant, too faint, or simply past that stage by the time we look. HOPS 315, by contrast, sits at a sweet spot in age, geometry, and observational accessibility. That is why astronomers can say, with unusual confidence, here, right now, is the very first step in the birth of rocky worlds around this star. It is a snapshot of a process our own solar system must once have undergone, captured not in hindsight from meteorites and models, but in real time, in the light of a star that is still learning how to shine. Inside the disk around HOPS 315, the real work of world building is happening in a narrow, turbulent ring of gas and dust close to the young star. This is not some distant outer halo, but a compact inner region roughly comparable in scale to the asteroid belt in our own solar system, where temperatures and densities are extreme enough to fundamentally change what matter is. Closer in, rock-forming minerals are blasted into a gas phase by intense heat. Slightly farther out, as the gas cools, those same minerals begin to condense back into tiny solid grains. The spectra that JWST and ALMA have captured from this region show exactly that kind of environment, signatures of vaporized silicate rock, together with crystalline minerals starting to solidify. It is as if we are catching the moment when an invisible chemical fog begins to turn into a storm of microscopic glass and stone. In this zone, collisions between grains are constant, dust sticking to dust, clumping into larger particles, then into pebbles and boulders. Gravity, turbulence, and drag from the surrounding gas all work together, slowly driving the system toward larger and larger aggregates. If this process continues, some of these clumps will decouple from the gas, settle into their own orbits, and grow into true planetesimals, the first seeds of a rocky planet. What makes HUPS 315 so remarkable is that we are not simply inferring this from theory. The chemistry we see tells us that the disk is actively cycling rock through fire and back into solid form, exactly in the region where a future Earth-like world could emerge. We are not yet seeing a baby planet as a distinct sphere, but we are watching the conveyor belt that will build it start to move, one layer of hot gas, one veil of condensing dust, one ring of nascent stone at a time. When astronomers look at HUPS 315, they are not just studying a random young star in Orion. They are, in a sense, looking into our own childhood. Many of the researchers involved in this work openly describe the system as a baby picture of the solar system, a snapshot of the kinds of processes that must have been unfolding around the newborn Sunday the 4th of May billion years ago. The parallels are striking. In HUPS 315, we see hot silicate vapor and freshly condensing crystalline minerals close to the star, exactly the kind of rock-forming material that would one day assemble into terrestrial planets. In our own story, those same silicate grains eventually built Mercury, Venus, Earth, and Mars. The violent winds and narrow jets blasting out of the inner regions of HUPS 315 echo the energetic outflows that likely sculpted our protoplanetary disk, clearing away gas in some regions, compressing it in others, and helping to define where different kinds of planets could form. Even the chemistry lines up. The minerals JWST detects around HUPS 315 resemble the silicates we now find locked inside primitive meteorites and comet dust in our own system. Those rocks on your shelf, those meteorites in museum cases, are the fossil record of a phase that HUPS 315 is currently living through in real time. The significance of this is profound. For decades, models of planet formation have been built from indirect clues and laboratory experiments, computer simulations of collapsing disks, measurements of meteorite composition, observations of older disks with clear rings and gaps. But they all had to assume what the very first solid grains looked like and how quickly they appeared. Now, for the first time, we are watching another star's disk at the exact stage when rock is just beginning to precipitate out of a hot gas, in the very zone where rocky planets are expected to form. That gives us a direct anchor point for our theories. It tells us that the condensation of silicates and the onset of solid planet-building material can begin very early in a star's life, and that the inner disk can already be rich in rock long before the system looks anything like a mature planetary family. In practical terms, HUPS 315 helps constrain how fast Earth-like planets can form and what initial conditions they start from, how hot the inner disk is, how much material is available, how turbulent the environment might be. In a more poetic sense, it lets us see our own origin story with fresh eyes. When we look at this young, shrouded star in Orion, we are watching a drama that our own atoms once played in, a ring of fire and dust slowly teaching itself how to become a world. When we look at HUPS 315, it is easy to feel as if we finally understand what is going on. Here is a newborn star, here is a hot inner disk, here is rock beginning to condense from gas. But in reality, this is just the opening frame of a very long story, and most of the plot is still unwritten. We do not know how many planets this disk will eventually build, or what kind of planetary family will live here in a few tens of millions of years. Will the system produce one or two large rocky worlds close to the star, with belts of debris farther out? Will massive gas giants form in the outer regions and then migrate inward, reshaping the orbits of smaller bodies like celestial bulldozers? Or will the disk slowly disperse before anything truly large can grow, leaving only a compact chain of small, dense, ember-like planets quietly circling their star? Right now, we are catching the process at its very first visible transition, hot mineral vapor turning into solid grains. Everything that comes next, the sticking, clumping, fragmenting, and regrowing of those grains into pebbles, boulders, planetesimals, and, eventually, fully fledged planets, lies far beyond our current observational timeline. To connect this first frame to the final family portrait of the system, astronomers will need both patience and new data. One major path forward is to use powerful radio arrays to search systematically for other young stars that look like HUPS 315. If we can find more protostars whose inner regions show the same signatures of hot silicate vapor and freshly condensed rock, we will know that this is not a rare, lucky snapshot, but a common early phase in the life of planetary systems. By mapping the cold gas and dust around many such objects, we can measure how much raw material is available, how it is distributed, and how often the conditions line up just right for rocky planets to begin forming so early in a star's life. At the same time, space-based infrared observations will keep watching HUPS 315 itself. By returning to the system again and again, astronomers can track how the detailed shape of its spectrum changes over time. Do the signatures of solid silicates grow stronger as more rock condenses? Does the balance between gas and dust shift? Are there hints that the inner disk is starting to develop rings, gaps, or asymmetries that could mark the birthplaces of future planets? Even subtle changes, measured over years or decades, can reveal how quickly the factory of solid material is ramping up and how violently the environment around the young star is evolving. In the broader context, HUPS 315 is only a first step. The real goal is a full statistical picture, dozens or even hundreds of systems caught at different ages, from the very first condensation of rock to disks already sculpted by newborn planets. With such a sequence, we could finally compare our own solar system's origin story to a whole population of others. Did the sun's disk behave in a fairly typical way, or was it unusually calm, unusually massive, or unusually long-lived? Are Earth-like planets a natural outcome of this kind of early mineral condensation, or the result of a rare chain of coincidences? For now, those questions remain open. HUPS 315 is not an answer so much as a promise, a sign that our instruments are finally sensitive enough to watch new worlds being written from the very first line. What comes after this first scene will be revealed only as we keep gathering light from these young, dusty cradles of future planetary systems. We are used to looking at finished worlds. Rust-red deserts on Mars, the icy rings of Saturn, the bruised clouds of Jupiter scarred by ancient storms, all of them feel complete, solid, already written. HUPS 315 shows us something very different, a story that has only just begun. Around this newborn star there are no planets yet, no continents or oceans, not even a single moon. There is only a bright, turbulent disk of gas and dust, and within it the very first crystals of rock are starting to appear, tiny grains that will one day be mountains, seabeds, and the cause of distant worlds. For the first time in history, we are not just inferring this moment from theory or reading it from the chemistry of old meteorites. We are watching it unfold in real time, in the light gathered by our telescopes. We see vaporized rock cooling and condensing into solid particles, the first building blocks of any future planet that might circle this young star. It is a quiet process, invisible to human eyes, but in those microscopic transitions from gas to crystal lies the beginning of everything a planetary system can become. When we look at the data from HUPS 315, we are not just learning about a faraway disk. We are looking into our own prehistoric past, to an era before Earth had a name, before there was sky, water, or life. Our entire world once existed in a similar state, a haze of silicate vapor and dust, slowly knitting itself into something that could hold oceans and, eventually, questions. That is what makes this discovery more than a beautiful image or a scientific milestone. It is a mirror held up to the moment our own story began. Somewhere in that glowing disk, grains are colliding, sticking, and growing, taking the first tentative steps toward becoming a world. And it is not impossible that, billions of years from now, on the surface of one of those worlds, someone will stand under an alien sky, look up at their parent star, and wonder how their home was born, just as we do now, watching the first dust of their future oceans and mountains come into existence.